you had no clue, most of you, how to face those integration problems, but you were able to see them and be like, oh, hey, this little Effie thing is super important. Yeah, it is. We got to yesterday, look at that problem where they gave us a derivative, a dy dx, and they were asking something about the original. That's integration, that's anti-differentiation, that's what we're talking about. That's a skill that we don't have yet. So let's develop it. Forever number 29 says, when you see an integral, now, this is the easiest way to see an integral. They tell you, hey, look, it's an integration problem. This forever card says, whenever you see an integration problem, we're not talking about word problems, not talking about when it's hidden in the meaning. We'll get there with applications once we develop this better. But if we see an integral problem, we have an integral sign, and we have the dx. Remember what I told you last week? I think it was last week. The notation has bookends. Sarah and Sean were fighting over this one a little bit. The notation has bookends. We don't read the bookends. What do we read? The books, right? Or if it's a sandwich, do you look at the bread to say what kind of sandwich it is? Okay, well, we like knowing what kind of bread it is, but that's not the type of sandwich. What tells the type of sandwich it is? Okay, so this notation, unlike a lot of math, has bookends. Now, there's deeper meaning to that, of course, and maybe we'll watch one more of those Essence of Calculus after we get a little bit more introduction. So you're like, okay, I'm familiar with it, but let's go a little deeper into why it is. But for right now, we're just going to say the notation has bookends, the integral sign and the differential. And inside is some sort of function. It better be in terms of the variable in the differential. This has to match, or else I cannot legally proceed forward. But once these variables match, what's in here and what's in the differential, I look on the inside and I say, hey, you're the derivative of someone. Who? You're the derivative, prime. You're the derivative of someone. Who? That's the antiderivative. Looking at an integral problem, whether or not they tell you this is a derivative, every integration problem, whatever they give you, whatever function is inside, when the integral is there, it says, look at this guy as someone's derivative, whose. And that function, the original to the derivative, the function whose derivative would match the integrand, is called the antiderivative. That plus c, okay, constant integration. That plus c, we barely introduced it last week, but I think maybe some of you held on to it. That plus c is necessary because if I ask you another question, very similar to the one we asked last week, what if I asked you for the antiderivative of 4x cubed, which I could, in my new notation, I could write this as find the integral of 4x cubed dx. We could rewrite it. One way is saying find the antiderivative. Another way is saying, hey, put that inside an integral. The notation says find the antiderivative. Either way, antiderivative. What would have a derivative of 4x cubed? Anybody got it? X to the fourth. Now, double check, just like, remember we talked about foiling and factoring? When you factor, you can check by distributing and see that it matches. Same thing here. You can check an antiderivative by deriving. What's the derivative of x to the fourth? Bingo, 4x cubed. However, what did I say last week?
It could be a constant.
Yeah, it could be a plus 1, a plus 12, a plus 23, a plus 792. It could be a minus 0. That's awkward, but yeah. It could be a minus 11. So what do we do to say, but we don't know if there was a constant because his derivative disappears? We put plus c. So plus c says could be a constant. Now, there could be times where it might be helpful for us to put a plus c1 or plus c2 or plus c3. Plus c, I usually just kind of absorb it in. I call it the arbitrary constant. It could be anything. It could be something simple, it could be something nasty. It could be x to the fourth plus ln of 2. The derivative of ln of 2 would be 0. We cannot know antiderivative. We could call it capital F. Because they gave us little f, we could call it capital F. The antiderivative, the original function, is going to somehow be an x to the fourth, possibly plus some sort of constant. And we could not figure out what the c is unless they gave us more information. Like, if they gave us an x and a y of the original function, we could solve for c. If they gave us a clue, an x and a y, sure we could solve for c, but otherwise we have to keep it arbitrary. We have to keep it unknown and just say, all right, I don't know, the constant's possible. Now, this function, 4x cubed, and the previous example that we did, 5x to the fourth, were perfect derivatives. derivatives of some simple polynomial. But we got to get a little bit harder. What if I was to give you something like this? I'll give you a second to write it down. The left side is a little tricky. We did one of these last week. The dy says, hey, look at the 1 as a function of y. Look at 1 as a function of y. This notation would technically be there's an f of y dy because of the y in the differential. I could think about this as a function of y. And over here I have an f of x times dx. Over on the inside. What would have a derivative of 1? Remember, antiderivative. Look at the function as a derivative of somebody but who?
X.
Except. What's our variable supposed to be? The differential tells me what variable to use. So you write the derivative of x is 1, but I don't have a dx. So therefore I say, well, fine. If it's a dy, the derivative of y is 1 as well. Times dy dx? No, it's okay. The dy is already there. And I'm not deriving anyway. The derivative of y would be 1. Times dy dx, the dy stays, the dx goes to the other side. Now pause. What would he come from?
Is it 3/5?
Not 3/5. Power rule. It's okay. We're building into rules. It's okay. You're not going to have to do this all semester. There are rules that are coming, forever cards that are coming, basic rules for integration. Okay. Power rule for differentiation says take away 1. Charlotte, what do you think?
And then it should be like the power should be 5 over 2. So it then can be there have a something like 2 over 5 times x.
Good. Charlotte got all the way to the answer. Let's pause and see if we can follow how she was able to get all the way to the answer of 2/5 x to the 5 halves. First of all, Charlotte, how'd you get to 5 halves?
So because I think the derivative is it is
And the power rule, you minus, good. You minus 1 to get to the power rule. So the original one is going to have to be 1 higher than what you're given. For derivatives, we take away 1. For integrals, we're going backwards, so we have to add that 1 to get back to where we were. But I didn't add 1. What did I add?
2.
Which is 1. I added 1. But I did it in a nice way where we can go ahead and say, oh, 3 halves plus 2 over 2 is 5 over 2. What did Charlotte have to think through when she was like, but the 5 halves, if I was taking a derivative, what would happen to this 5 halves? It would come down. There's nothing there. So if this came down and went away, what had to be waiting for it? It's reciprocal. Now the cool thing is, if I was to ask you to take this example, let's just see how it works. Remember the essence of calculus video? Could you have come up with this on your own? I'm not necessarily asking if you can come up with all the theory behind how this works, or like all of the area under a curve, but could you just think about, given this example, could you make up a rule for when you have, in general, the integral of any x to the n dx? What do you guys think we could make as a rule?
1 over n plus 1, and then like x to the n plus 1 or something?
X to the n plus 1 is a great way to start because you have to add 1, seeing the power. This is a power rule or a result of a power rule. So I have to add 1, but I have to multiply by the reciprocal. That's one way of putting it.
Wait, why would it just be 1 over n instead of n plus 1?
Because the n's not what's coming down. That's already the derivative. This is what needs to be derived. The n plus 1 is what's coming down. Same thing here. When we were trying to get to this function, the new power is what came down, not the old power. Does that make sense? And the cool thing is with that, guys, that's exactly the power rule for integration. Ooh. Let me give you a second.
Ooh.
Let me give you a second.
Ooh.
Let me give you a second. Let's go ahead and write down this first and let me zoom in on the rules. Now, the nice thing is you don't have to write both sides. I'm just going to write down the integration formulas. I'm not going to write both sides. I'm just going to have you write the integration formulas. This chart, I believe, is in your book. If you do want to maybe write the integration, go back and get the derivatives. But I do want you to write down first that the basic rules are all founded on the idea that any integral problem says whoever's inside that integral is the derivative of someone. And that someone is called the antiderivative plus the arbitrary constant such that if I was to take the derivative, let me put it this way. I don't like this notation, it's too early. It's too early for you guys. If I was to take I'll put it this way. That's a little bit better as far as what you're going to be seeing. When you have the integral of a function, the answer is going to be the antiderivative, and I can always check the antiderivative because when I derive, first of all, the constant 0, and when I derive, you'll get back to what was on the inside. You have the rule correct if, when deriving, you get back to the original. So I could go ahead and put the c, but the derivative of c ends up being 0, so it's gone. And then once we have that foundation, we can actually take a lot, not all, I know, I'm so sorry, a lot of our rules. We can actually take a lot of our rules and go backwards.
So we're doing all the integration formula?
Yeah.
Thank you for zooming in.
So you don't necessarily need to write all of the differentiation formulas. These are the derivatives you already know. But look, if the derivative of c is 0, then we can say the integral of 0 is c. Oh, that's weird. The integral of 0 is c. If the derivative of constant multiple, k times x, kind of power rule constant multiple. The derivative of k times x is just k. Bring down the 1, the power disappears. And the integral of just a constant k will be kx plus c. And then it goes on from there. Let me give you some time. I'm not sure that my saying the rule is going to be helpful, but as you write it, those of you that, like David, we were talking about, like hearing it, you could read it as you write it. Kind of say it to yourself as you write it. That might be helpful.
Oh, I'm gonna run out of room.
In your comp book?
No, on this page.
Oh, don't worry, we have plenty more. You could do 2 columns if you want the integration formula.
Yeah, except I wrote too big.
Look, it's really interesting.
Yeah.
Power rule, we already kind of figured out. There is an exception to the power rule. Write that exception. That's going to be interesting to figure out. But some of you could actually plug in -1 and maybe figure that out, why it's an exception. But what's also going to be interesting and a little tricky is derivatives backwards. Coming straight out of the derivative rules. But just like the unit circle, we had to know them in pre-calc well enough to go forwards and backwards. Gotta know the trig derivatives well enough you can go forwards and backwards. Common weakness of kiddos that don't study their formulas enough. P.S. Why is there all of a sudden a yellow box around the formula?
The argument. Oh, Misty. I mean, the regular version.
We're gonna take this
I don't
one
have
apart.
Hold on, let me see how many cards I split it into last year. Might have just been 1 if I was being really crazy. But I think we might have a couple that are coming up a little later, so let me check out our forevers real fast. And I'll get them updated at the same time. Go team. it kind of crazy though? Do you guys think that maybe at least one or two of those integral problems you could now do with these formulas?
Oh, yeah.
Not all.
I mean,
There's still most.
used as a formula.
Yeah, not all. Some are a little bit tricky. There's this thing called mu sub, which is kind of like chain rule backwards, but not as comprehensive. You can at least somewhat understand what you're looking at now, which is kind of cool. Because in one day we kind of broke the barrier. A couple days, I suppose. So we have forever number 29, definition of an antiderivative, right? Antiderivative. And then this will be forever number, I think, 30.
31, 32.
Let me double check. I think it's 29 and 30. L'Hopital's definition of antiderivative. Good, good, good. Okay. There are just a few of these basic ones that will make a new card. And I'll show that to you as soon as I get the forever card updated. And if you guys think about derivatives, I mean, number one, derivatives, we made the trig rules totally separate. And this one, I see the trig rules as a bit more basic because of all the work that we did do with the derivatives. The integration will be a little bit more basic. Yeah, while I'm getting the forevers, that's a good time. However, exponential and logs, I don't call that basic. Actually, a lot of colleges don't even include transcendental functions, aka inverse trig, exponential, and logarithmic. Don't include that in their Calc 1 course at all. They don't cover any inverse trig, any exponential, any logarithmic, because the proofs for these formulas, the proofs behind these formulas and the ones for inverse trig are much more complicated. So they see it as a higher level. But let me show you the forever card real quick, shut up before I see the question. So the forever card, the first one is going to be everything up to the end of trig. Okay, so go ahead and split your box underneath cosecant, cotangent is the last one. So I'm going to put a yellow line underneath the trig. Exponential and logarithmic, we should probably make that delineation. So we're going to have forever number 30, which is all the ones up through the end of trig. So there's that delineation. And then we're going to have forever number 31, where we're specifically talking about exponential and logarithmic integration rules. Ooh, these are very fuzzy. I need a better picture of these. Okay. So then you guys can see the other forever card. It's just going to be 3. Except it's not our 32. I think it's our 31. Ooh, that's ugly. What's going on? Hi, buddy. There we go. There we go. But it's 31, not 32. I apologize. Does that make sense? As far as where we're delineating? Let me put it in our notes so that we have it all nice and marked. Forever number 30. Forever number 30. Question, will some of you guys catch on to this quick and be like boom, 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 going super fast? Within a small amount of time. Yeah. Well, others of you need Just slowly take it one problem at a time, having the formulas right next to you, applying them until you get used to them. Yeah, and that's okay. That's not a bad thing. Do what you gotta do. Because the ones that go too fast, some people that memorize quickly also forget quickly. We have to keep on reviewing over and over. Those of you guys that take the time and practice slowly. Digging deep into the formulas in a sense. Hold on to it usually a little bit better and longer. Now, hold on, pause. Question. What trig integrals end up with a negative answer?
Sine.
Cosecant squared, cosecant cotangent, and sine. Why do these three? That's weird. Wait a minute. In derivatives, it was derivative of anything with a c, anything with a c, anything with a c. Why is sine in that mix?
Because cosine.
Because the derivative was of cosine. So think antiderivative. It's based on the antiderivative. The antiderivative is cosine. Wait, derivative of co is negative. Oh. Derivative of cotangent should have been negative. It's not there. Derivative of cosecant should have been negative. It's not there. So that's something that even for me, I have to think about. Integral of sine. Wait, cosine, derivative of cosine is a negative. Negative! I still go through that process. Some of you might have a faster way of memorizing or remembering. But this is definitely going to be a little bit tricky as far as when to put a negative. These ones are easy because they're still c's, but the integral of sine is cosine. Wait, derivative of co is a negative. Got it. Got to put that in. What else looks weird as you guys were writing? There should be one more that's kind of like, wait, what?
E to the x.
Yeah, well, actually he's nice though. Let me zoom in on him. The derivative of e to the x was e to the x, right? So what's the integral of e to the x? Yeah. So not only is the derivative of e to the x, the integral of e to the x is e to the x. He's still our nicest guy, as long as there's not a 2x, and then we have to wait until we learn more. But the integral of e to the x is e to the x. Nice. How about a to the x? Was he a nice derivative? Was he as nice as e to the x? No. So his integral is going to be, remember, e to the x, a to the x. They both have derivatives, aka antiderivatives, that are the same. But a to the x needed an ln of a, which means, I needed 1 over ln of a to compensate. Because if I was to take the derivative, if you want to see it, if I was to take the derivative of a to the x, it has an ln of a. So if I was to take the derivative of this guy, it would be ln of a to the x over ln of a. Cancels. Very similar to the power rule for integration, how I have to divide by that constant. Same thing here. I have to divide by ln of a to get rid of him. And then last but not least, this one looks a little confusing. Let me show you why. You might want to do a quick little other way of looking at it. Couldn't you rewrite 1 over x as x to the negative 1?
Yes.
Well, then, why couldn't you just use power rule?
Because it's not equal to -1.
It says negative 1 doesn't work, but why? It's actually really nice. We don't just have to memorize negative 1 doesn't work. Negative 1 doesn't work. What if we were to do the power rule? I would add 1. What's x to the negative 1 plus 1? All over. Wouldn't that be x to the 0 all over 0? Is that an answer? No, that's an undefined. Oh, so it doesn't work. No. Who has a derivative of 1 over x? ln does. ln does. And here's the reason why there's an absolute value. ln of x, remember, ln has a restricted domain. Basic graph. Come on, we do forever. Basic graph. Doesn't it just work for x greater than 0, ln? X greater than 0, right? Okay, here's the dilemma. 1 over x. Isn't he all real numbers but 0? So if I'm taking the integral of something that has both a right greater than 0 and a left less than 0, I can't just all of a sudden only have an answer that works for only half. The absolute value says, hey, he'll model this guy. This antiderivative will work for this guy. If I put an absolute value, ln will now work on the right and the left. So then I've gone ahead and made it legal. This has domain of all real numbers but 0. ln wouldn't, so I have to put the absolute value so that ln of x also works for negatives and positives when put in. Making them all positives works for everything but 0 as well. So it's all a domain problem.
So if it didn't have an absolute value, it wouldn't work.
It only have half the answers when it needs to have all of them. Does that kind of make sense? Okay. So what was this all to show? Sometimes you're going to think the integral of 1 over x is a power rule. But what's going to happen when you actually go to solve? You're going to be like, wait, it doesn't work. Exactly, because it's not power rule. It's ln. Okay? With that, let's go play with these, huh? Now, when we go to play with these, I'm gonna do this right now. Yeah, let's do this real quick before we can play. Stink. Tomorrow will be our big play day. As far as playing with the rules, probably whiteboards out, all that sort of stuff.
Love that. Are we supposed to bring whiteboards to class?
No, remember I had the teacher protect them.
Markers back. You told us like next.
I was thinking next semester, but so far we're still okay on markers. But I still have a few boxes up there, so I think we're okay.
I think Austin brought like a packet of course, so I'm just gonna hop on that.
Yeah, he did. Always the answer to an indefinite integral, family of antiderivatives. Family of antiderivatives, what we're talking about is this plus c. What I have in parentheses, I'm just trying to describe what an indefinite integral is. Indefinite means an integral without bounds. I think we typed in an integral once or twice to our calculator. And when you typed in an integral to your calculator, calculators can only do definite integrals. AKA, it has little spots for you to put in a lower number, like 0, and an upper number, like 5. And that would be for a certain function. If it did have 0 to 5, we'd be finding, like you kind of saw the guy do in the video. 0 to 5 tells us what area to find a finite area of or under a function. Now, we're not doing area right yet. We're not connecting the pieces. Right now, we're just playing with the antiderivative, going backwards from integration. But definite integrals is where we're headed. But right now, we're just doing indefinite integrals, where the answer to an integration problem is not a number. That's why your calculator can't find it. It's an equation. It's an antiderivative. So what I'm trying to show you with the whole family of antiderivatives is, if you're able to have an antiderivative plus c as your final answer, there are some differential equations, aka some problems needing integration, where the plus c won't end up as just a plus c. It's going to end up kind of all mixed in the function. So we'll see that when we get to expand a little bit further. But if it's just a plus c on the outside, this is actually going to be identified as a vertical translation. Remember, adding on the outside of any function is going to be a vertical translation. Which means if I was given, for instance, a basic graph of f of x plus 0, let's just say we had something funny, like, I don't know, there we go. And let's say this was f of x alone. Well, as soon as I had f of x plus 1, all that would happen is everything would shift up 1. So all of a sudden I have the exact same graph. Pretend it's the exact same graph. Struggle. The exact same graph, but up 1. Or the exact same graph, but now maybe up 3. Or the exact same graph, but now up 5. So all these family of antiderivatives, if I was to actually show you guys a sketch, or it could be down 1, or down 2, or down 3, it's going to be a family of antiderivatives, meaning I'm not sure exactly which one is the right one. I just know that all of these are options. So I was kind of telling you, when you get one antiderivative, as soon as you put plus c, you actually are putting a whole family. But what's similar is that they behave in a similar way as long as you have antiderivative plus c as your final answer. And at the very end, this is a quick little note. You can only find an actual c when given a clue, when given a point. When given a clue or given a point. And then the last concept, that derivatives and integrals are inverses of each other. The nice thing is, in that Essence of Calculus video, he explained that it's actually a very involved idea. to take something that we call the fundamental theorem of calculus, which is not our goal right this second to cover. We're going to wait to cover that one until we get a little deeper into integration and how it's tied to area under curves. Don't delay. Nah, we need some people just to have a little bit of time to play with integrations and antiderivatives. So one problem solving clue, that's the first one. You can only find C when given a point. They give you a point suite. Start here and then say, hey, I have an X to plug in and a Y to plug in. I can find you your C for that specifically. Because in this whole family of antiderivatives, if we were to choose a particular point that then defines, that limits, specifies exactly which one. So as soon as they give you, for instance, a point, we call that point x1, y1. We already come up here to the family of antiderivatives. That x1, y1 would only be on one curve. And if they gave us an x1, y1, then we could say, oh, hey, you mean this guy. Oh, yeah, okay. So if they give you a point, it establishes one set one as the answer and not all of them. And the other idea we'll definitely go into more depth on. Okay, kiddos, we're just going to play a little bit, enough to let you get into homework a bit. We're just going to play a little bit. You have the rules. Let's play. Let's play. Let's play. Those of you that think you can do this well, aka Tyler, you've been practicing this for a while now. Have fun with number 2, just don't say anything out loud. Number 1, what rule do you guys think? Yeah, power rule, I agree. Power rule, I agree. So you can go ahead and think about, all right, x to the 14, how does the power rule work? You have to think about, it came from being 1 power higher, right? X to the n plus 1. The formula says 1 over times 1 over, or all over, 14 plus 1. Why? Because this would need to come down when you derive. But the problem is, wait, who's chewing? 3. So let's see if this makes sense. What if I had 3 over 14 plus 1 is 15 times x to the 15th, which is the same thing as 1/5. Would this work? How can you know for sure? Bring down the 15. What's 15 over 5? Take away 1, x to the 14. So, very similar to differentiation, constant multiple rule. It works for integration too. We can leave the 3, and we can deal with the variable expression. And that's actually one of your rules, isn't it? Pull out the k. So we could have technically rewritten this to be, we'll deal with the 3 later. Let's look at the x to the n right now. Does that make sense? We just kind of left the 3. Now number 2 gets a little weirder. Because guys, in any of those rules in that table, did you see a square root of x?
No,
But radicals are just different ways of writing fractional exponents. Just like we did with derivatives, let's rewrite, because isn't that really just a power rule? And integration, just like derivatives, we can deal with addition and subtraction. There's a sum and difference rule separately. So if it helps you, we can rewrite this, splitting up into each of its pieces, and then take it one piece at a time. Like x to the 1/2, that's x to the n. I could add 1. You guys see why I'm adding 2 over 2?
Yep.
What would 1/2 plus 2 over 2 be? 3 over 2. Wouldn't it be nicer just to kind of get in a pattern of multiply by the reciprocal without having to do the whole yucky like divided by 1/2 plus 2? Now, you might want to say plus c, and I understand why you would do that. We could do plus c, but I'm going to do plus c1, and here's why. Because the next integral, I have the integral of sine is cosine. Give me 1 second. It's a negative cosine, which means I have to make that a plus. But wouldn't this guy have his own c as well? Well, if I do one arbitrary constant plus another arbitrary constant, I get a third arbitrary constant. So I could really just have 2/3 x to the 3/2 plus 3 cosine of x. And guess what? A constant's a constant, a constant. We'll just call him our C. So you don't have to write multiple C's, just make sure there's one at the end. Great job, kiddos. Go ahead, play with some of these formulas, come back tomorrow to practice and improve. Sound good? Alright.
Yeah,
Oh, in the
I did some of them, the integral one.
Nice. I figured that you'd play with them.
Yeah, mostly just the definite intervals, because they're pretty easy. Some of the harder ones.
Yeah, they put the easier integrands in the definite for sure. Because they figured there's that extra step.
Like at the end, it started to be
Like chain rule, right?
yeah.
Yeah.